Hello, my name is Shelby Howerton, and this is my lab for oscillations. In my presentation, I'll be discussing how I observed a real-life system, created the computer model in GlowScript, and then compared my real-life observations to the computer model. Then I would discuss the physics principles involved. The first goal in this lab was to implement the energy principle, which gives us delta E is the total change in kinetic energy equals the change in kinetic energy plus the change of potential spring energy plus the change of gravitational potential energy. I will then analyze the given video and tracker and find positional data, which I will use in GlowScript to find the kinetic potential spring energy with the formulas listed above. With this, I'll be able to update the total velocity and position data, and I can compare my timestamps as well. And then lastly, I'll use the computer model to show the observed data. Here's a description of the system and the surroundings. I know that there is both X and Y direction movement, so I oriented tracker by setting the origin of the spring's attachment point. I calibrated the video with the known length of the strength spring. My initial position was found in the table at the bottom right corner, and my initial velocity was 0 because the weight on the spring started from rest. The period of oscillation was 1.164 seconds, and I found that by taking the average of the times. The first 3 oscillations that I got by looking at both the time versus X position and time versus Y position graphs. In my GlowScript model, I used an average of the periods of oscillation obtained from both the time versus X position and time versus Y position graphs. This was to obtain the best period of oscillation for both the X and Y directions. If I use an average of the first 3 oscillation periods from the original graph, there would only be a lower accuracy in the model, and vice versa. It is important to use the average since the value of T affects both K and the spring force, and then the net force as seen here. I initialized my GlowScript programs, the weight's mass, the position, initial velocity, and the video's time range from tracker. And the initial time range, the initial time was 0, and then the timestamp was 1/210, which is seen in the video frame, and then I uploaded that into tracker. The observed transitional data from the model can see the X and Y position from tracker, and then I imported the CSV file with the data points from tracker. G was the universal gravitational constant, K is the spring constant, and L naught is the length of the relaxed spring. These values were found from manipulations of existing equations. K was calculated from the formula below, where T is the period of oscillation and K is 7.62. L naught was calculated with the equation L, the current length of the spring, minus the mass, times GK. With everything I plugged in, L naught equaled 84 meters. S is the spring potential energy equation and is equal to the magnitude of L minus L naught at the bottom, and then at the bottom of the slides are the code for finding the different energies according to the equations on the goals of the lab site. The only new one was E, which stands for total energy, and is calculated by adding up the kinetic, gravitational, potential, and spring energies. In the while loop of the code for each step, I calculated the gravitational spring forces to find the net force. I updated the object velocity and position from this data, and then updated the spring information based on the new position on the weight of the end. And I calculated the kinetic, gravitational, spring, and total energies and their changes in the GlowScript program. This is my GlowScript program with the animation, which shows the model ball in blue and the experimental position in red. You can see the paths are very similar, indicating that it's a pretty good representation of the observed position. This graph shows the position of different energies with spring potential in green, gravitational potential in red, kinetic in blue, and total in orange. And you can see that the changes in spring and gravitational potential energies are mirrors of each other, while the change in total energy is 0. Lastly, you can see the graphs of the model in blue versus experimental in red positions for both the X and the Y positions. As you can see, the change in energy versus time graph above shows that the total energy stays at 0 during the duration of the observed model motion, meaning in this case the sum of the changes in gravitational potential, spring potential, and kinetic energies are 0. Because of this, we know that there are no outside forces acting on the system and the energy principle is satisfied. Here are the 2 position graphs produced by the model X on the left and Y. The model should have been equally accurate in matching the experimental positions for both the X and Y positions due to the period being the average of the periods calculated from both data sets. However, you can see that the data is slightly better matched And this could have been due to the fact that we should have recalculated the period for the most accurate results. We could have used a better camera so that the original time frame on tracker was better, and we could have improved the calculations. In conclusion, we were able to satisfy and improve all of our original goals for this experiment.